A parallel plate capacitor has two plates with dimensions 20 centimeters by 30 centimeters that are separated by a 1 millimeter gap, and a 12 volt battery is connected across the two plates. So in part A, what is the capacitance of this parallel plate capacitor? So the capacitance, the equation is epsilon naught A over D, where the epsilon naught is the constant, that's 8.85 times 10 to the negative 12th, times the area of the capacitor. It's 20 centimeters by 3 centimeters, which we'll have to convert those into meters. So 20 times 10 to the negative 2 by 3 times 10 to the negative 2, divided by the distance between the plates, which is 1 millimeter, or 1 times 10 to the negative 3. And that is equal to 5.3 times 10 to the negative 11 farads. Or if you wanted to put it into prefix notation, that would be 53 times 10 to the negative 12 farads, which is 53 picofarads. Part B, what is the charge on each plate? And the equation that relates charge to capacitance and voltage is Q equals CV. So the C we just figured out is 5.3 times 10 to the negative 11 times, and it's connected across a 12 volt battery. So when you multiply those, you get 6.37 times 10 to the negative 10 coulombs. And if you want to put it in prefix notation, that would be 637 times 10 to the negative 12th, or 637 picocoulombs. For part C, how much energy is stored in the capacitor? Since we know the charge, because we just figured it out, and the capacitance, because we figured that out in part A, and the voltage, because that was given, we can actually use any of the equations to get the energy. And those equations were 1/2 QV, 1/2 CV squared, and 1/2 Q squared over C. So if we had not figured out the charge in part B, I'll go for the equation that does not have the charge in it, which is that second one, 1/2 CV squared. So the UC is equal to 1/2 CV squared, which is 1/2 times 5.3 times 10 to the negative 11 times 12 squared, which is 3.8 times 10 to the negative 9 joules, or if you want to put it in prefix notation, that is just 3.8 nanojoules. And for part D, on this figure, which is the side view of the capacitor, draw a diagram of the electric field between the plates, showing its direction, assuming that the top plate is the positively charged plate, and the bottom plate is negatively charged. And then determine the magnitude of the electric field. So the electric field just goes from positive to negative, so we'll just draw some parallel lines going straight downward. On a true capacitor, the outer lines kind of tend to go, kind of bow out slightly like that. But for the most part, the lines are going to be parallel. And then the electric field, the magnitude is V over D, where V is the potential difference, or the voltage, which is 12 volts. D is the distance between those two plates, which was 1 millimeter, or 1 times 10 to the negative 3, which is equal to 1.2 times 10 to the 4th newtons per coulomb, or volts per meter.